Hello all, welcome back to Electronic Device and Circuits video lecture series. I am BVV Sachinarayana, Associate Professor in Department of ECE, Eastern Institute of Technology, Bhimavaram. In unit number 3, Rectifiers and Filters, we already discussed about introduction to RPS, basic rectifier setup, off-wave rectifier operation and waveforms, center-adapted full-wave rectifier operation and waveforms, bridge rectifier operation and waveforms, and we already derived some characteristics of a rectifier. In this video, I am trying to derive the expressions for ripple factor, gamma, peak inverse voltage PIV, transformer utilization factor TUF of a rectifier. The objectives of this lecture are calculation of ripple factor, calculation of peak inverse voltage, calculation of transformer utilization factor of a rectifier. The seventh characteristic of off-wave rectifier is ripple factor, and it is denoted by gamma. The output of off-wave rectifier is not perfect DC. It is pulsating in nature. That's why we can call it as a pulsating DC. The output of off-wave rectifier consists of a pulsating component, which we can call it as a ripples. Ideally, in the output of the rectifier, there should not be any ripples. So, the measure of such ripples present in the output with the help of a factor called ripple factor, denoted by gamma. So, this ripple factor gamma represents how smooth the output is. The ripple factor expresses how much successful the circuit in obtaining pure DC from the AC input. Smaller the ripple factor, closer is the output to pure DC. So based on this, we can define the ripple factor. Ripple factor is defined as the ratio of RMS value of AC component in the output to the average value of DC component present in the output. So you can write gamma equal to RMS value of AC component in the output by average value or DC value of output. So this gamma, we can represent it as IRMS dash by IDC. So IRMS is the RMS value of AC component in the output, and IDC is the average or DC value in the output. So in general, the total current of the output is given as total current component equal to DC component current plus AC component current. I already told the output of the rectifier, it consists of both DC and AC components. So this we can represent it as the total current I equal to the DC component IDC plus the AC component. I am representing it as a I dash. From this, I want AC component, so I dash is equal to I minus IDC. So based on that, we can easily calculate IRMS dash. That IRMS dash is the RMS value of only AC component. So IRMS equal to IRMS dash is equal to. So if you want to calculate the RMS value, first squaring, then calculate mean and apply square root. So I already calculated the AC component current, which is equal to I minus IDC. So first squaring this value. So I minus IDC square. Then calculate the mean. So it can be calculated by using integration over complete cycle. So integral 0 to 2 pi d omega t and divide with base, that is 1 by 2 pi. Then apply the square root. So with this, we can easily calculate IRMS dash. So expand this I minus IDC whole square, that equal to square root of 1 by 2 pi integral 0 to 2 pi I square minus 2IDC into small I plus IDC IDC square into d omega t. Then this IRMS equal to IRMS dash is equal to, then expand. So the first term is, this is I square. The first term is 1 by 2 pi integral 0 to 2 pi I square d omega t. That is the first term. Plus the second term is 2 into IDC, it's constant. So IDC into integral 0 to 2 pi I d omega t plus the third term IDC square integral 0 to 2 pi d omega t. And very clear, this 1 by 2 pi, it is common to all terms. Then this is first term and this is the second term and this is the third term. So the first term, it becomes 1 by 2 pi integral 0 to 2 pi I square d omega t, which is equal to IRMS. We already calculated. So it's I square. So it's IRMS square. Okay. So in general, there is a square root. Now there is no square root. That's why I'm calling it as IRMS dash square. Similarly, the second term is 1 by 2 pi integral 0 to 2 pi I d omega t, that equal to IDC. And the third term is 1 by 2 pi integral 0 to 2 pi d omega t, which is equal to 1 by 2 pi into 2 pi, that equal to 1. So if you substitute all these things in the above equation, then IRMS dash equal to square root of IRMS square minus 2 into IDC into IDC, that is 2 IDC square plus IDC square. So IRMS dash equal to square root of IRMS square minus IDC square. So from this IRMS dash, we can easily calculate the ripple factor gamma, which is equal to IRMS dash by IDC. So ripple factor gamma equal to IRMS dash by IDC. IRMS dash is already calculated, that is square root of IRMS square minus IDC square by IDC. So you can write like this: IRMS square minus IDC square by IDC square. So gamma equal to square root of IRMS by IDC whole square minus 1. This is the general expression for the ripple factor of any rectifier. From this, we can easily calculate the ripple factor of half-wave rectifier. For half-wave rectifier, the ripple factor gamma is equal to square root of IRMS by IDC whole square minus 1, and IRMS equal to IM by 2 for half-wave rectifier, and IDC equal to IM by pi for half-wave rectifier. Substitute these two in the general expression, then factor gamma is equal to square root of IM by 2 by IM by pi whole square minus 1. So this IM and IM it cancelled out. So gamma is equal to square root of pi by 2 whole square minus 1. So the gamma of a rectifier is equal to 1.211. So here gamma means AC component by DC component, which is equal to 1.211. From this, AC component equal to 1.211 into the DC component. So from this, we can say that the ripple contents in the output of a rectifier is more than the required DC component. So half-wave rectifier is not a good rectifier. There is more AC component and less DC component. Then the next parameter of half-wave rectifier characteristics is peak inverse voltage. PIV. So this PIV is defined as the maximum reverse voltage that a diode can withstand without destroying the junction. So the name itself says that it is the maximum voltage across the diode in the reverse biased condition. The PIV across a diode is the peak value of negative half cycle. For half wave rectifier, the PIV of the diode is Vm. So this PIV is the peak voltage across the diode in the reverse biased condition. So let me draw the diagram. So this is the in reverse voltage. So this is the diode used in the rectifier circuit, and for this we are applying the AC signal, and there is a load RL. So here the input is negative half cycle. If we consider the negative half cycle, during this negative half cycle, the diode D is reverse biased, and it can act as a open circuit ideally. So all the input voltage, that is minus Vm, must be dropped across the diode only. Means the diode, it must withstand for this negative half cycle voltage. So that voltage we are calling it as a peak inverse voltage. So in this case, what is the current flowing through the circuit? Means the current flowing is 0. Since the input is negative half cycle, the diode is reverse biased, no current is flowing. So no voltage is dropped across the load. So all the voltage must be dropped across the diode, reverse biased diode. So the diode, it must be withstand for this reverse voltage. That's why for half wave rectifier, the peak inverse value of the diode is Vm. So we can say this peak inverse voltage occurs at the peak, at the peak of each negative half cycle of the input. The peak of the negative half cycle of the input signal. Okay. So for half wave rectifier, we know that VDC equal to Vm by pi. We already calculated. So from this, Vm equal to pi into VDC. That is the PIV of diode used in the half wave rectifier. PIV of the diode used in the half wave rectifier. So what is the importance of this peak inverse voltage? Means the diode used in the rectifier circuit is selected based on this PIV rating. Diode must be selected based on this PIV rating. So suppose we are selecting a diode which is less than this PIV rating, then the diode, it's may damaged out. Why? Because in the negative half cycle, all the input voltage must be dropped across the diode. So we must select the diode based on this PIV rating. Then The ninth characteristic of a rectifier is transformer utilization factor, TUF. The factor which indicates how much is the utilization of transformer in the circuit is called TUF. This TUF is defined as the ratio of DC power delivered to the load to the AC power rating of the transformer secondary. So, for calculation of this TUF, we need DC power delivered to the load by AC power rating of the transformer. AC power rating of the transformer. So we can represent it as a PDC by PAC. It's not AC power, it is a PAC rated. That is the transformer rating, transformer power rating. Okay. And we know that this PDC equal to IDC square into RL. Whereas the PAC rated is equal to VAC of RMS into IRMS. So the current flowing through the circuit in terms of RMS value is IRMS. If that IRMS is multiplied with the voltage rating of the transformer secondary RMS value, then we are getting PAC rated. The transformer secondary feeds the AC power to the rectifier. So it is necessary to determine the rating of the transformer while designing a power supply. And that power rating, it can be calculated from this TUF. So first I am trying to calculate PAC rated, then PDC, and their ratio, it gives the transformer utilization factor. So PAC rated equal to VAC RMS into IRMS. So VAC RMS. First I am calculating this one, and multiplying those two, we are getting PAC. So VAC RMS equal to, so here it is a root mean square value of the AC signal voltage. So the minimum value is 0, the maximum value is Vm. So squaring both, then find out the average, means plus by 2 and apply square root. So the maximum value Vm, minimum value 0, and squaring and find out the average value and apply square root, then we are getting VAC of RMS, so which is equal to Vm by root 2. Vm by root 2. And IRMS for off wave rectifier, we already calculated the same current, it is flowing through both load, transformer secondary, and diode. So IRMS equal to Im by 2. So PAC RMS is equal to Vm Im by 2 root 2. So that is PAC RMS. Similarly, calculate PDC. Power delivered to the load, it is equal to, I already told, it is IDC square into RL. We already calculated IDC for off wave rectifier, which is equal to Im by pi, and substitute this in the above expression. So PDC equal to Im by pi whole square into RL, where Im equal to, I already calculated, that is Vm by Rs plus Rf plus RL. So from this we can calculate Vm also, that Vm equal to Im into Rs plus Rf plus RL. Okay. So I already calculated PAC rated and PDC. So their ratio, it gives the transformer utilization factor. So TUF equal to PDC by PAC rated. So PDC, it is Im by pi whole square into RL divided with Im by Vm into Im by 2 root 2. Okay, and I already given equation for Vm. This is Vm. So convert this Vm to Im, then our TUF is equal to Im by pi whole square into RL by Vm. Vm means Im into Rs plus Rf plus RL multiplied by Im divided with 2 root 2. Then this Im square, Im, it is cancelled out. So the TUF, we can represent it as 2 root 2 pi square divided with Rs plus Rf by RL plus 1. Rs and Rf are the internal resistance of secondary winding and diode forward resistance, which is very, very small compared to RL. So we can neglect Rs plus Rf by RL. Rs plus Rf is far less than RL. So neglect Rs and Rf. Those are the internal resistances, very, very small. So the total term Rs plus Rf by RL is very, very small compared to one we can neglect. So the TUF is equal to 2 root 2 by pi square, which is equal to 0.287. That is the transformer utilization factor in off wave rectifier. So very clear. This TUF means PDC by PAC rated or RMS value, which is equal to 0.287. From this, we can easily calculate the AC power rating of the transformer, that is PAC rated or RMS is equal to PDC by 0.287. So this is the power rating of the transformer required for off wave rectifier. So here the transformer utilization factor of off wave rectifier is 0.287, which is very, very small. It shows that in off wave rectifier circuit, the transformer is not fully utilized. So PDC equal to 0.287 into PAC rated means very small portion of transformer is utilized in converting AC to DC. So TUF is very small for off wave rectifier. Transformer is not completely utilized. And coming to the summary, in this lecture we have learned to calculate calculation of ripple factor, calculation of peak inverse voltage, calculation of transformer utilization factor. In the next lecture, I am trying to derive the expression for voltage regulation, form factor, peak factor, advantages of off-wave rectifier, and disadvantages of off-wave rectifier. Thank you all.